Hello, this is Jack Jackson. We're back again working some more Taylor's series. So find the Maclaurin series expansion for f of x equals cosine x. The way I want you to do this is to actually use Taylor's theorem directly. Remember, Taylor's theorem says back here that we can take the kth derivative at a, divide it by k factorial times x minus a to the k, sum that from k equals 0 to infinity, and we get a Taylor series. If it's a Maclaurin series, that just means it's centered at 0. So this would just become x to the k, and this will become specifically the derivatives evaluated at 0. So work that out directly like we did this one for sine of x in the last video, and do that for cosine. See if you can do that yourself. Come back when you think you have an answer. Press pause now. So like I said, this is very similar to the one that we did last time for sine of x. Once again, we get a four function repeating cyclic pattern here for the derivatives. The zeroth derivative, our original function, is cosine of x. The first derivative is then minus sine of x. The derivative of that is minus cosine of x. The derivative of that is sine of x. And the derivative of that is back to cosine of x. So the fourth derivative is back at the beginning, then the fifth, sixth, seventh derivative, then back to the eighth derivative at the beginning, and so forth. So one way to express this is with the mod notation. So if x is congruent to 0 mod 4, that is, when you divide x by 4, you get a remainder of 0. In other words, x is a multiple of 4. Then the that should not say x, it should say n. Let's fix that. That same problem appeared in the last video. Those should have been n's instead of x's on that. So if you're watching the last video, you should go back and make that correction. So here it is corrected so that these say it's the power that matters here, not the input x. So if the power is congruent to 0 mod 4, then the not the power, but the order of the derivative is congruent to 0 mod 4. You get cosine of x. If at the nth derivative there, where the n is congruent to 1 mod 4, the remainder when you divide by 4 is 1. Then the nth derivative is the opposite of sine x, and so forth for these others here. Now remember, of course, we want to evaluate at 0, and cosine of 0 is 1 and sine of 0 is 0. So this time, all of the odd power terms disappear, and we're left with only the even terms. If it's even but not a multiple of 4, we get -1. Even but a multiple of 4, we get 1. Okay, so what are we going to get? We just get we get x to the n over n factorial. So x to the n over n factorial, but we also either get a plus or minus 1 with that. And so the only terms, though, that remain are the even terms, right? So we get the first one is 1, and then there's no x term. We get x squared, but it's going to have a -1. And of course, that's over 2 factorial. Then the cube term is 0, so it's gone. And then we get 1 over 4 factorial x to the 4th, back to +1, and so forth. So ultimately what you see here is you only get the even numbered terms, and you just got the same term power. The power on the term is the same as the what you put with the factorial on the bottom, but we get an alternating sign. So we could express that this way right here. To get the even numbers, you just have 2k. We'll get you an even number for k being all the possible whole numbers here. Starting with k is 0, you get 2k is 2 times 0 is 0, x is 0 is 1. So that's just the constant term, which you do get in this series. And then we only get the even powered terms here. Then whatever the power is, you put a factorial with that down here in the bottom. And then we get an alternating sign. And if we put -1 to the k, that will start with a positive and then go negative, positive, negative, positive, negative, alternating like that, so that all the multiples of 4 there are positive. Let's see, positive, negative, positive. Whoops. Let's fix that. I got off one there. The negatives are on the ones that are even but not multiples of 4. And then we get positive on the other ones. And make sure I've got that positive, negative, positive, negative, positive, negative, positive, negative, so forth. Okay, so there we go. Should be alternating in sign. Positive, negative, positive, negative, positive, negative, positive, negative. That's correct. Positive, negative, positive, negative, positive, negative, positive. Next one would be negative, and so forth. So there you see several terms kind of worked out. This is all worked out with the numbers here, worked out in the factorials there. So ultimately only end up with even power terms there. To show that this is actually equal to cosine of x, we need to look at the, well, first of all, we need to see what domain this thing even converges on. So we're going to use the ratio test there. So we plug that in here, put in the sort of the general term here, and then the next one here that's not 0, we ignore the 0 terms like we've done here, and put in k plus 1 up here. This should be, something's wrong there. This should just be 2k here. Okay. Yeah, I think that's right. So this is 2k, x to the 2k here, x to the 2 times k plus 1, which is 2k plus 2. So that's going to give us an x squared when that cancels. The negative ones we don't really worry about. The absolute value, that's all going to be 1, so that goes away. This is going to go to the bottom. That's 2k plus 2 factorial. That 2k factorial flips up to the top. 2k plus 2 factorial is 2k plus 2 times 2k plus 1 times 2k factorial, which cancels with that 2k factorial, leaving just this. That limit there is 0 regardless of what x is. And so this one converges for all real numbers. To show that it converges to the cosine function, we need to look at the limit of the remainder term. That remainder, it looks like this. That derivative there is either going to be plus or minus sine or cosine, which is always between -1 and 1. The absolute value of that's always less than or equal to 1. So this gets us down to this point here. And when you plug in a specific x value, here we have an exponential function, which grows fast eventually, but not nearly as fast as this factorial down here. So this limit is going to go to 0. So we see that the following series expansion is what we have, and I bet I have my sign problem down here too. Yep. There it is fixed. So cosine of x is this sum from k equals 0 to infinity of -1 to the k over 2k factorial times x to the 2k, which is written out this way here. And there's some of the terms worked out. All right, time for you to try another one. Try to find a Taylor theorem. Use it to find a Maclaurin series expansion for f of x equals sinh of x. See if you can determine the interval of convergence and prove that it converges to the original series. Press pause now. Well, remember the derivative of sinh of x is cosh of x, and the derivative of cosh of x is sinh x. Cosh of x is the hyperbolic cosine of x. I'll show you the definition for it here in a minute in terms of the exponential function e to the x, and the same thing for sinh of x. So we get this two function pattern here. So if n is even, the nth derivative is sinh of x, and if n is odd, with the nth derivative cosh of x. Now evaluate at 0, sinh of 0 turns out to be 0, and cosh of 0 turns out to be 1. In general, the definition of sinh of x is 1/2 e to the x minus e to the minus x. Plug in 0 there, you get 1 minus 1 is 0 times 1/2 is 0. Cosh of x in general is 1/2 times e to the x plus e to the minus x. Plug in 0, you get 1 plus 1 is 2 divided by 2 there is 1. So again, sinh of x is 0, and that's going to happen for the, you're going to multiply that as part of the coefficient for the even terms. So all the even terms are going to be annihilated. They disappear, not going to be present. Only the odd terms remain, and the derivative part of this only approximates or only has a 1 there with it. So what's left is only the odd terms here, x, 1 over 3 factorial x to the third, 1 over 5 factorial x to the fifth, and so forth. And here's some of those things worked out. And if we use the ratio test, we determine the domain is a set of all real numbers, and we can show that the remainder term approaches 0 as k approaches infinity. If you finish those pieces on your own, they're extremely like the last couple of examples, so I'm not going to work them out here, that we show that this is exactly sinh of x for any real number. Similarly, we can work this out for cosh of x. It's a very similar setup. So once again, we just get this two-cyclic pattern here, starting this time with cosh of x when n is even, and then going to sinh of x when n is odd, evaluating at 0, cosh of 0 is 1, sinh of 0 is odd. So this time it's the odd terms that are going to disappear, leaving only the even terms. So we get x to the 2k divided by 2k factorial, which you can see this worked out starting with k equals 0. So starting with 1, which is a 0 degree term, then a second degree, 4, 6, and 8. Only the even powers are left, and this does converge to cosh of x for x's being any real number. And so we can use the ratio test to determine the domain's a set of all real numbers. We show the remainder term approaches 0 as k approaches infinity. So this really is converging everywhere and is converging to cosh of x. Now, this gives some interesting relationships among the following series. E to the x we cited was the sum from n equals 0 to infinity of x to the n over n factorial. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, and so forth. Sine of x, well, let me go down to sinh of x. Sinh of x is just the odd powered terms of the e to the x. Look at that. See? Cosh of x is just the even powered terms of the e to the x expansion. Sinh and sine of x are the same thing, except that the sine has alternating signs and the sinh doesn't. And cosh and cosine are the same, except the cosine has alternating signs and the cosh doesn't. So it's kind of an interesting thing here. So one of the things that points out is if you add sinh and cosh, you should get e to the x. Well, that's true when you look at the series, but that it's also true pretty easily from the definition. Sinh of x is 1/2 e to the x minus e to the minus x. Cosh of x is 1/2 e to the x plus e to the minus x. So just distributing here, we get 1/2 e to the x minus 1/2 e to the minus x plus 1/2 e to the x plus 1/2 e to the minus x. That one with the minus x's cancel. These double up, so you get 1 times e to the x, which is, of course, just e to the x. So it turns out that both sinh and sine are odd functions, and they ended up only having odd numbered powered terms. And the cosine and cosh were only the even numbered terms, even powered terms, and they're even functions. Remember, remind you that an even function is a function where f of minus x is the same as f of x, and that's the same as having y-axis symmetry. An odd function is saying that f of minus x is the opposite of f of x, and that's the same as being a function with origin symmetry. So it turns out in general that it's an odd function if and only if the Maclaurin series only contains odd powered terms, and it's an even function if its Maclaurin series only contains even powered terms. Okay, and so we've seen some interesting relationships among these basic things. There's actually an interesting connection from this to complex analysis, doing calculus and so forth with complex numbers, and we'll do a little bitty short video on that a little bit later on as well. So maybe it's time to practice finding some Taylor and Maclaurin series, some homework problems.